Good day, ladies and gentlemen. My name is Carel Kruger and I'm the project leader for the RTIMS research project on cyber-physical systems. I will be presenting on the work completed thus far to implement a deployment of interconnected industrial Internet of Things devices in the in-stope area. I'm going to start the presentation with a short introduction to RTIMS and how this research project entitled Cyber-Physical Systems fits into the bigger picture. The aim of RTIMS is to create a standardized, open source and royalty-free industrial Internet of Things platform for which the mining industry and original equipment manufacturers that will allow the reuse of industrial Internet of Things applications developed for mines across mining operators. This will ensure more efficient investment of mining research and development funds, while allowing the original equipment manufacturers to build products and applications according to the standardized platform. Mining operators, as well as their suppliers and integrators, will thus be able to adopt these original equipment manufactured products with an increasing measure of confidence due to guaranteed interoperability with existing equipment. This project specifically focuses on the raise, gully and drill face areas where blasting and scraping takes place. The stope has traditionally been poorly instrumented, although there is a wealth of information and opportunity for optimization. The poor instrumentation is mainly due to the harshness of the environment and the associated cost of installing and maintaining infrastructure in a section of the mine which constantly advances and is disregarded once the ore has been extracted. Technology produced by this work package thus needs to be wireless and battery operated, with intrinsic safety certification to withstand the harsh environmental conditions while guaranteeing safe, reliable and continuous operation. This project contributes to the RTIMS Industrial Internet of Things core platform by focusing on the research and product development required to deploy a network of interconnected industrial Internet of Things devices, specifically designed for in-stope applications. This network of interconnected devices is called a cyber-physical system. The cyber-physical system uses sensors and actuators to collect data and respond to events based on a specific algorithm. An example of such an algorithm may include the optimization of productivity metrics, such as the tonnage of ore mined, the number of blast cycles produced, or the shift and the maintenance conditions of running equipment. The project contributes to the RTIMS Industrial Internet of Things core platform by focusing on the research and product development required to deploy a network of interconnected industrial Internet of Things devices, specifically designed for in-stope applications. The network of interconnected devices is called a cyber-physical system. The cyber-physical system uses sensors and actuators to collect data and respond to events based on a specific algorithm. An example of such an algorithm may include the optimization of productivity metrics, such as the tonnage of ore mined, the number of blast cycles produced for that shift, and the maintenance conditions of running equipment. The cyber-physical system can also be used to implement systems responsible for enforcing safety based on a miner's location, or alternatively assist with gathering and reacting to real-time data to improve seismic monitoring and ventilation, to name a few. This project was initiated by identifying a suitable reference architecture for the system to be designed, as well as a final vision which is used to guide the research and development activities. The Industrial Internet of Things reference architecture was adopted together with a three-layered approach consisting of cloud, fog and mist level devices, as per the figure. According to the Industrial Internet of Things reference architecture, any Industrial Internet of Things system should make use of a three-layer design where each layer consists of a shared data bus. Each layer is independent of the surrounding layers but connected to the adjacent layers. The in-stope cyber-physical system can thus be defined as a collection of mist layer devices connected via fog gateways to the cloud. Gateway devices provide the localized processing power which is used by the mist to implement the desired in-stope optimization application. A baseline version of the in-stope cyber-physical system is shown and will be developed further as part of the Agile approach, which will be used to achieve the final vision. A summary of work units required to achieve the final cyber-physical system is shown. The hardware reference design and the in-stope emulator were prioritized as the work units are required to progress using the Agile research and development methodology. I will give the audience a few seconds to familiarize themselves with the work units before transitioning to the next slide. The first version of the RTIMS emulator is shown in the picture. The emulator is capable of running the exact same software as the real-world devices and is thus a faithful representation. The emulator can thus be used to evaluate promising open source technologies for inclusion in the RTIMS Industrial Internet of Things platform. The emulation above shows two MIST networks, each deployed in a separate stope. The two MIST networks communicate via separate gateways to a server. The ability to evaluate cyber-physical system algorithms in an emulated environment is similar to the idea of first simulating a design before building it and is an invaluable tool to save time and money. A reference design is an effective method to assist product integrators to understand the system and perform integration into established products which could benefit from being part of the RTIMS ecosystem. A first version of the hardware reference design was completed and is shown. A wireless low-power development kit from Atmel was selected and lightweight machine-to-machine remote firmware upgrades implemented. The Leshan user interface is also shown, which is connected to the development kit and allows for simple remote firmware upgrades and device management. The entire toolchain to program the development kit, as well as the Leshan server and lightweight machine-to-machine standard, are open source technologies, adhering to the use of open source components and the open design philosophy of RTIMS. The final vision of the RTIMS cyber-physical system research project has been defined and broken down into smaller work units. The work units need to be completed in order to realize the final vision of an in-stope cyber-physical system. Although some work has been done, a large backlog of research and development work needs to be completed before the final vision for the in-stope cyber-physical system can be achieved. The recommendation is to continue with the current vision as funding is available, making use of the Agile methodology to complete the work units as described. Ladies and gentlemen, this is the end of my presentation. Thank you for listening and showing interest in the in-stope cyber-physical system project. Please feel free to make contact with the RTIMS Program Manager, JJ Vernage, if you require further information on the work presented. So long and thank you for all the fish.